With an intensifying water cycle through the effects of climate change, large-scale flooding is becoming a more frequent hazard. In this chapter, you will learn how to detect floods using remote sensing technology. A good example of this issue is a large-scale flood in North Rhine-Westphalia, Germany in 2021. Look at the flood map by the DG ECHO of the ERCC to assess the scale of the damage. This method requires advanced filtering and few functions to visualize the spatial extent of the hazard. In the second half, you will assess further damage to people, agriculture, and urban area. Similar to previous chapters, we use time variables and a selection within the map using a polygon to set up the filter. This time, however, there is two time variables, before and after the flood event. Additionally, we need to set the polarization of the satellite. For our analysis, the VH, or vertical-horizontal polarization, is required. This way, we include vertical and horizontal waves to create the SAR image. VH is generally recommended for flood mapping due to its heightened sensitivity to land surface changes, whereas VV is more responsive to vertical structures, making it suitable for distinguishing open water from land, such as in shoreline detection or identifying large water bodies formed after flooding. The path direction depends on the region of interest. Some regions are covered by both directions, but some are only covered by one. Choosing the correct path direction avoids false positive signals by different viewing angles. A predefined threshold of 1.25 is used, where values above 1.25 are assigned a value of 1, and those below 1.25 are assigned a value of 0. This binary raster layer represents the potential flood extent. The threshold of 1.25 was determined through trial and error, and may be adjusted if there are high rates of false positives or false negatives. After setting up these parameters, we can list them in the collection filter for later use. But before that, we must select the study area in the map using the polygon tool. The instrument mode is set to IW, or interferometry wide swath, due to its wide coverage of 250 kilometers and high spatial resolution of 5 meters by 20 meters. In the next cell, we define the collections of satellite images as the before and after collections, with our previous set time parameters. This also separates before and after flooding images. By defining dates, metadata is being extracted from the GEE data to verify the dates we filtered for. Just to be sure, let's print the amount of tiles and dates we now filtered for our selected area. Radar images often contain speckle noise, which is reduced using a focal mean filter with a radius of 50 meters. This smoothing helps in better analysis by reducing noise. With the difference calculation, we make a big step towards our results. By calculating the ratio between after and before images, we will identify changes in the SAR images. Now, by masking and using the threshold of 1.25, potentially flooded areas are located and used to visualize the extent of the flooding. Water bodies, like lakes, can be misinterpreted as flooded areas, which is why with the next line of code, we will mask out those permanent water bodies. For that, we can use the Global Surface Water Dataset available in GEE. To further reduce noise, connections and flooded will remove isolated pixels. Only areas connected to at least 8 neighboring pixels are retained. Since floods do not occur in steep areas, we can use a digital elevation model and a threshold of 5% to further cancel out possible errors by masking out those areas. Finally, with a flood pixel area, flood stats, and flood area hectare, we finalize the process and calculate the flooded area. To give this another dimension, we visualize our findings. Damage assessment. Now that we know the amount of flooded area, we can begin our damage assessment by calculating the exposed population, agriculture, and urban area. Population. For assessing population damage, we can load population density data, mask and compare it with the flooded areas, and calculate the amount of people exposed to the flooding. Agriculture. The same goes for agriculture, only that the dataset for this assessment will be MODIS data to identify croplands and identify affected agricultural areas by flooding. Urban area. MODIS data also allows us to filter for urban areas. We will use LC again, but this time class 13 to identify urban areas, mask them, and calculate exposed areas. With the final visualization, we can assess flooded areas and their damage to population, agricultural land, and urban areas. Use the layer panels to activate or deactivate the visualizations.